Hello dear students, welcome to Learning Chemistry is Easy and Fun, a channel dedicated to making chemistry easier for any learner of chemistry. The topic we are dealing with today is structure of atom, lesson 18. Now coming to the electronic configuration of the atoms, how do we configure or how do we arrange the electrons in any atom is what is called as electronic configuration. Just like the students in a school are distributed on the basis of their learning level, on the basis of the knowledge that they already have, same way the electrons in an atom are governed by certain rules. In this particular lesson, we shall be dealing with those rules and also will go on to explain the electronic configuration. The first rule that we will talk about is the Pauli's exclusion principle. Pauli's exclusion principle states that no two electrons can have all four quantum numbers the same. Now, if you are not clear about the quantum numbers, lesson number 17 is completely dedicated to quantum numbers and how do we decide and what are their values. What are quantum numbers? Quantum numbers are simply like in your school, you have class values. So, you have class 1, class 2, class 3. Now, in class 1 also there are sections, so 1B, 1C, 1D. So same way these electrons, as we said, according to Bohr they are present in the orbits. Later on quantum mechanical model said no, they are not present in orbits, they are present in orbitals, and these orbitals are part of sublevels. So we have the S sublevel with 1 orbital, we have the P sublevel with 3 orbitals, we have the D sublevel with 5 orbitals, so on and so forth. Now, applying the Pauli's exclusion principle, we shall see how the electrons are present and how many electrons can be present in any sublevel as well as the orbital. To make the things faster, a bit faster, I have already listed them over here. So, if you have, we shall be listing the electrons on the basis of the L, N, L, M and the spin quantum number. N principal quantum number, azimuthal quantum number, magnetic quantum number, the spin quantum number. For the first energy level, that means N, the value of N is 1. So, the value of L will be, yes, it's 0, S sublevel. This has only one orbital because the value of M is 0. The number of values of M gives us the number of orbitals, yes, in any sublevel. Now, as we said, there can be only two possible spins, plus half and minus half. So, we have 2 electrons over here. In other words, my 1s orbital has 2 electrons. Let us see a case that if we add one more electron to this 1s orbital. So, if I am talking about 1s, N is 1, L is 0, M is 0, S is one electron will have plus half, the other electron will have minus half. Supposing I add another electron to this. Now this electron, N will be 1, yes, because it's the first energy level. L will be 0, yes, because we are talking about the S sublevel. M will again be 0 because the value of M is dependent on the value of L. So M is also 0. Now the spin quantum number. Spin can either be plus half or minus half. If the spin of this electron is plus half, that means its all 4 quantum numbers are the same as of this electron. If On the other hand, it has a spin minus half. In other words, this electron will have all 4 quantum numbers as of the second electron, which goes against the Pauli's exclusion principle, which says that no 2 electrons can have all 4 quantum numbers the same. So, what we deduce from this is that the maximum capacity of an orbital will be 2. Yes, you cannot have more than 2 electrons in any orbital. Come to the second part now. So, when we are talking about the second energy level, here that means the value of n is 2. Can you try and list down the values of L and M without seeing what is listed over here? Go ahead and give it a try. It will be helpful if you recall what we have done in lesson number 17. Yes, when n is 2, that means I am talking about the second energy level. The value of L, again, it is from 0 to n minus 1. So, L is 0. We are talking about S sublevel. L can also be 1. So, what sublevel does it correspond to? Yes, it corresponds to P sublevel. Corresponding to L equals 0, what will be the value of M? Yes, 0. So, S sublevel has again got only S orbital, and S orbital will have 2 electrons with opposite spins plus half and minus half. So, a total of 2 electrons in this. Coming to L is equals to 1, corresponding to P sublevel. Now, on the basis of L equals 1, what are the possible values of M? Yes, it starts from minus L to plus L, all integers, right? If you remember, this was there in lesson number 17. So, based on this, the values of M will be minus 1, 0 and 1. Now, when I have minus 1, again the values of S can be plus half minus half. M is 0, plus half minus half. M is 1, plus half minus half. In other words, my P sublevel will have 1, 2, 3 orbitals in all. These orbitals all have equal energy, and the term used for them is called as degenerate. And each orbital in turn can accommodate 2 electrons. So, 2 here, 2 here, 2 here gives me a total of 6 electrons. So, the second thing that I deduce from the Pauli's exclusion principle is the maximum number of electrons in a subshell. So, S, the maximum capacity is 2. P, again, yes, we did it in the previous lesson also, it is 6. Please remember, here I am talking about subshell, there we spoke about orbital. The maximum capacity of an orbital remains 2. But because P has 3 orbitals and each orbital can accommodate a maximum of 2, this gives me a value of 6. Let's go back to D now. Would you like to try D yourself first? That means when I am talking about n equals 3, go ahead and give it a try. So, what all sublevels will be there in n equals 3, that means in the third energy level. If you notice over here, first energy level had only 1 sublevel, second energy level had 2 sublevels. Third energy level, n equals 3, when the principal quantum number is 3, the value of L will be 0, 1, 2. So, I am talking about S, P and yes, D. Now, corresponding to each one of them, there's a 0, -1, 0, 1. So, in other words, s orbital. These are the 3 p orbitals corresponding to the d sublevel now. The value of L is 2. So, the values of m can be ±2, ±1 and 0. So, how many orbitals are there in d? Yes, it's 5. And 5 times 2, because the capacity of each orbital is 2, gives me a total of 10. So, this gives me the maximum number of electrons in the d subshell as 10. Can you tell me what will be the value of L for F sublevel? So, if the value of L for S is 0, P is 1, D is 2, for F it is? Yes, it is 3. So, the value of M comes down to ±3, ±2. So, when you are talking about F, an additional set of 2 values gets added up. So, the maximum capacity of F sublevel comes to 14. So, with the help of Pauli's exclusion principle, we are able to predict the maximum number of electrons in any orbital, the maximum number of electrons in a subshell, and the interesting part is it also gives me the maximum number of electrons in any energy level, because we know that the maximum number of we have seen that the maximum number of orbitals is n square, and each orbital can take in how many electrons? 2. So, the maximum number of electrons in any energy level comes to 2n square. I am sure you will be able to relate to your learning in previous classes where you simply said that the maximum number of electrons in any energy level is 2n square. So, if you have n equals 1, we had maximum number of electrons as 2. If you had n equals 2, maximum number of electrons is 8. When n is equals to 3, what is the maximum number of electrons? Please calculate. Pause the video. Please try and calculate. N equals to 3. So, the maximum capacity of the third energy level will be how much? Yes, it's 18. So, that's how you get 2, 8, 18, 32 and so on. Let us now go on to the second principle, which helps us to decipher or decide the electronic configuration of any atom. It is called as the Aufbau principle, a German word meaning building up. So, we will be building up the configuration of the atoms. Now, this building up takes place on the basis of certain rules. Aufbau principle says electrons are filled up in the order of increasing energy. How do I decide what orbitals have higher energy and what will have lower? This is first stated on the basis of n plus L rule, which says that any orbital having the lower value of n plus L will have lower energy. If there are orbitals which have the same value of n plus L, then the one having lower value of n has a lower energy. Let us see an example of this. 1s, 2s, 2p. Pause the video, try and fill this table yourself. I will give you one example here. If I am talking about 1s, so the value of n is 1, s means the value of L is 0. So, what is 1 plus 0 equals? Yes, it is equals to 1. Try similarly for 2s. So, the value of n will be Yes, 2. The value of L will be 0 because why 0? Because I am talking about 2s sublevel over here. So 2 plus 0 gives me a value of 2. Now on the basis of this, we will see that when the electron will enter, it will enter 1s first followed by 2s. So your 2s sublevel has higher energy than 1s. And Aufbau's principle says electrons are filled up in the order of increasing energy. Now let's compare. So we had compared 1s and 2s. Now let's compare 2s and 2p. 2p means n is 2. What will be the value of L over here? Because I am talking about P. So be careful. What will be the value of L over here? Yes, L will be 1. So 2 plus 1 gives me a value of 3. So when I am comparing 2s and 2p, which of these has lower energy? Yes, 2s. So I have the order of filling up as 1s, 2s, 2p. Let's continue our investigation further. I've got 3s, 3p, 3d, 4s, 4p. I leave it to you. I'll give you a small hint over here. L, the value of L for an S sublevel is 0. For P it is 1. For D it is 2. And for F it is 3. Go ahead and fill this table. Pause and do it. Yes. Are you ready to tally your answers? N is 3 over here. L is 0. So I have N plus L is 3. 3p. N is again 3, but L is 1. N plus L is 4. 3d. N is 3. L will be, yes, it is 2. Gives me a value of 5. N is 4. L is 0. N plus L is again 4. Because this is 4s. That means the value of L is 0. N is 4. P is 1. Gives me a value of 5. So comparing 2p and 3s. So what comes higher? Yes, 3s is higher. Now compare 3s and 3p. So it is 3p which is having higher energy. So till now we have got 1s, 2s, 2p, 3s, 3p. Now let us compare 3p and 3d. N is 3, L is 2, N plus L is 5. Yes, so 3d has higher energy. Coming to 4s. N is 4, L is 0, N plus L is 4. Oh, look at that. The value of 4s is smaller than that of 3d. Yes, something of a difference over here. So yes, we'll apply the N plus L rule. So 1s, 2s, 2p, 3s, 3p, and instead of the electron going into 3d, we will have the electron going into 4s. Followed by, yes, let us see. Now come to 4p. N is 4, L is 1, N plus L is 5. Yes. Now, if you see over here, my 3d and 4p, both of them have a value of 5. So, which one has the lower energy? Go back to the second part of the rule. Lower N plus L, lower energy. Yes, we've been following it up till now. If N plus L is the same, then the one which has lower value of N will have lower energy. Yes. So if I have 3D and 4P, both of them have the same value of N plus L. So which will have lower energy, 3D or 4P? Yes, it is 3D. So I have 1s, 2s, 2p, 3s, 3p, 4s, 3d. right? So this way we can build up what we call as the Aufbau table. Simply write it as 1s, 2s, 2p in the next line, 3s, 3p, 3d in the third line, 4s, 4p, 4d, 4f in the fourth line, 5s, 5p, 5d, 5f, 6s, 7p, 6d, 7s, 7p, 8s. Now just write it like this. This is not the order. What's the order of the energy levels? Draw the arrows. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 8s, and so on till we find the elements which require higher electronic configuration. This is the simplest way of drawing the Aufbau table and remembering it also. It would be better if you can practice a few times so this becomes easy for you to write the electronic configuration of the elements. Coming to the next principle, which decides the electronic configuration of the elements. It is called as the Hund's rule of maximum multiplicity. Simple. If a mother has 3 children and she has 5 bread pieces with her, she will prefer to give first one piece or one loaf to each child and then see who needs more, right? The same thing or the same rule applies for the behavior of the electron distribution as well. What does the Hund's rule say? It says that electron pairing begins only and only after orbitals of equivalent energy have been singly filled. So we know that S sublevel has only one orbital. P sublevel has 3 orbitals and they are all of equal energy, and as we said earlier, these orbitals of equal energy are called degenerate. They are all having equal energy. Now, coming to D sublevel has 1, 2, 3, 4, 5 orbitals. F has 7. Yes. So, the maximum capacity of S sublevel is 2. Maximum capacity of S orbital is also 2. First, the electron enters singly and then pairing begins. Coming to P. When I have to write the electronic configuration or we have to put the electrons, we are not going to put it like this. The second electron will not go into this box till the other boxes have had one electron each. So, according to Hund's rule, the electrons will first go into each of these orbitals singly and then pairing. So, if we have to enter a 4th electron, this is how it will enter. A 5th electron, a 6th electron. Same for the D. The electron has to enter first. Each of the D orbital will acquire 1 electron. After each one of them has acquired 1 electron with parallel spin, now if I have to add 1 more electron to it, the electron will start pairing up the unpaired electrons. You will understand more of this when we write the electronic configuration of the elements. This is what is called as Hund's rule of maximum multiplicity. Why and what justifies this? We shall be doing it a little along with the fourth point, which says that fully filled, half filled and completely vacant orbitals are extra stable. The explanation that we are going to give now justifies the Hund's rule as well as the fourth point. Simply what it says is that if you have the orbitals as half filled and the electrons are having parallel spin, they are not of the opposite spin. That is also part of the Hund's rule, that the electrons which occupy them should have parallel spin. Now when these electrons have the parallel spin, they can keep shuttling. It's like you are confined to this hall, and there are 5 children which are put in a room. So what they can do is they can keep on changing places. So 1 change, 2 change, 3 change, 4 change. So the first electron can exchange places with 4 of them. The second electron, of course we've talked about this, the second electron can also exchange places with the other 3. The third one can also exchange places with the other 2. So with each exchange of their orbitals, energy is being released, and that is called as exchange energy. So when you have these half filled or fully filled orbitals, the exchange energy is high. On the other hand, if let us suppose I have got an arrangement like this, right? Now what happens is the exchange energy is minimal because these are already paired up. They will not undergo exchange. These are completely vacant. There is nobody here. So with whom will this child play, right? So the exchange energy becomes lower. So we have fully filled, half filled and completely vacant orbitals are extra stable. Also, by filling up the orbitals half or full, there is a symmetry of the distribution of the electrons in any orbital, and anything which is symmetrical will be much more stable than something which is not. If you see, P is not symmetrical, the alphabet A is symmetrical. So with symmetry, the stability is much more. In the next lesson, we shall be talking about the electronic configuration and the applications of these concepts to write the electronic configuration in terms of S, P, D and F, which is a point of worry for many of the students. If you've liked the video, please don't forget to subscribe to the channel and share it with your friends, because sharing is caring. Have a nice day. Happy studying to all of you.